please welcome him with me to deliver his lecture, A New Sky, JWST, and the Early Universe.
Thank you very much. Thank you. Thank you. There will be nothing so high-tech as a colander this evening, I promise. When I started putting these lectures together for this year, and this is the last of the 6 that I get to deliver from this stage for this year, one of the things I really wanted to get across was that astrophysics, science in general, is a living subject, that things are changing, that the science we encounter often at school or online or in the newspapers, which is a sort of fixed collection of facts that one is supposed to learn, is very far from the truth, and that the joy of this subject is that it's changing, and that there are new things being discovered and questioned and queried every day. This is the second lecture in a row where I've had to do a rewrite the day before because of new discoveries. And I'm going to show you some images that were released only yesterday. And in fact, the main subject of the talk was based on data that was released only last month. So while I hope you've all got the message that science is a living subject, I'd like to ask my colleagues at this point to slow down, at least for the next year. The other thing that's unified this year's talks is a focus on the machines, the instruments, the marvelous feats of engineering that make our discoveries of the universe possible. And I think often when we focus on the instruments, we sort of get this impression. This is sort of the hero shot of a single scientist in a clean room with the golden mirror of tonight's topic, the JWST, or James Webb Space Telescope, as the agencies would like us to call it. And this is obviously a fantastic image. The texture that you can see reflected in the hexagonal mirrors there is actually just the wrinkles on the clean suit of the single scientist standing there. But these things are built by teams. And JWST was a dream that began in the late 1980s and which was built by literally thousands of engineers and astronomers over the course of many decades. In fact, it was notoriously, for many years, the most delayed project in world science, and it was being delayed at a rate slower than time was passing. Things were really bad. But it launched in 2021 on Christmas Day, and now we get to talk about the science. But I wanted to start by acknowledging the contributions of everyone who makes this marvelous mission happen. So, what happens when you point the world's most expensive telescope into space? Well, yesterday we got this image. And honestly, I was tempted to just spend an hour talking about the richness of this one field of view. Let me give you some sort of sense of what we're looking at here. This is a tiny patch of the sky. That's the first thing to say. A patch of the sky centered on a cluster of galaxies, systems of hundreds of billions of stars like our own Milky Way, which are themselves about 4.5 billion light years away. That's a long way away. I don't have an intuitive way to explain that to you. It's just a long way away. It's in the southern sky, and the cluster's called Abell S1063. It's not significant enough to have a more interesting name. But the galaxies of the cluster are the sort of, not orange, but sort of yellowy, diffuse shapes you could see mostly across the middle of this image. And that cluster has come together over about 9 billion years of cosmic history, with galaxies colliding and being shaped by gravity to form this immense city of galaxies. It's a much denser environment that we in the Milky Way find ourselves in. But you've probably already noticed that in addition to those yellow galaxies, there are red streaks across this system. In fact, they seem to circle the center of this image. Those are more distant galaxies. They're light magnified and bent by its passage close to that nearby galaxy. So the setup is something like this. You have a distant galaxy. It emits light. Its stars emit light into space. That light spreads out, but as it passes the nearby galaxy or the nearer galaxy, it's lensed, it's bent relativity tells us, Einstein lets us calculate the degree to which it's bent, and we end up with these distorted images of galaxies. Often the technical term used for this is sluggification, where you take a nice, beautiful, round galaxy or a pancake-shaped galaxy, and by the time it's been lensed by this imperfect telescope, you end up with a stretched arc. But yet, we can see these distant galaxies, and their light. Actually, let's switch from distance to light travel time. So their light for these distant galaxies has probably mostly been traveling towards us for about 10 billion years. So in a universe that's 13.8 billion years old, you can see that this lens is letting us look back towards the distant universe. And we can do all sorts of interesting physics with this as well. We can, for example, if we work out the degree of lensing, the amount by which this light is bent, how sluggified the galaxies are, we can weigh the nearby cluster and get a sense of how massive it is. So we can do some physics here as well. Now, like all JWST images, this is taken in the infrared part of the spectrum, and we can see that that makes a difference by comparing to the Hubble Space Telescope image of the same galaxy. So until yesterday, this was the best image of this region of space that we had, and you can see, yes, that many of the same features are there. The galaxies at the center are there. There are now blue streaks in this image, which represent the lens galaxies, though there are many fewer of them. But really, the difference that you should have noticed between the two is that this field is much more crowded than in the optical. So if you use telescopes and cameras that are sensitive to the light that we can see, you get this Hubble Space Telescope image. If we switch to longer wavelengths, to the infrared, then you get this much more crowded scene. And it's calculated that in the deepest images that JWST will take, we expect that 45% of the pixels should hit a galaxy that's detected. So at these wavelengths, and with a telescope this powerful, space is no longer black. We're looking at the sky with a backdrop of distant galaxies. Now, as a reminder, we're in the infrared, so we go from the optical and then towards longer wavelengths, you go infrared, microwave, and then radio. And we're here in the infrared region of the spectrum. And astronomers have long known that this was useful. In fact, it was an astronomer, William Herschel, who I realise comes up in an awful lot of these lectures, but William Herschel, who showed that such a thing as an infrared part of the spectrum exists. He did a very clever experiment in which he took light from the sun, passed it through a prism so it became a rainbow, and then he put thermometers at various points in the rainbow to measure the different energy content of the different colours of light. But he also put a thermometer out beyond the red, where his eyes couldn't see any light, and he discovered that that thermometer too still heated up. And so there's still energy there outside the visible spectrum. And that was the first, in 1800, the first scientific demonstration that there was more to light than meets the eye, that there were wavelengths that we couldn't see. Infrared can be observed from the ground, that experiment shows that, but to get to the broad range of wavelengths that it covers, you want to be in space. And of course, that's what we have JWST for. That's also why it has this bling, this golden mirror, which I always like telling people this is the most expensive telescope ever built, then pointing out the mirror is coated in gold. But there are good scientific reasons for that. A, it's not much gold. And B, it's just a very thin coating, and B, gold reflects the infrared really well and has good thermal properties, so if it's heated up it doesn't flex. So we have these hexagonal mirrors, each of which can be individually adjusted to try and keep the mirror perfect. And then the whole thing was launched by a European rocket and sent off to an orbit about 1 million miles away. So unlike the Hubble Space Telescope, this is a telescope that can't be repaired. It will have a 20-year lifespan, extended because of the precision of the rocket launch, but that will be our lot. That will be our observing capacity with JWST. And it's not just that things look different in the infrared. The infrared lets us see different places. So, for example, I'm not going to make this a general lecture about JWST science. That would take a whole series. But on the left is a famous Hubble Space Telescope picture of the Eagle Nebula. So this is a place often called the Pillars of Creation, where within that dust that blocks out the starlight that you can see there, that dark material, it's cold enough that gas and dust can collapse under its own gravity to the point where new stars can form. And you can see sort of at the top of one of those pillars, new stars are emerging. Once they form, their winds and their activity and the pressure from their light frees them from their cocoon, and this will slowly erode away as new stars form. In the infrared, we see colder parts of the universe. And so we're able to see inside the pillars. So on the right there is the JWST picture. And what we're seeing, although they're clearly the same structures, is we're seeing more of the places where the stars are actually being born. You can see the clumps of material that surround the sites of new star formation. And so one thing we can do with this, as well as looking at these distant galaxies, is we can look at places where stars are forming. And I'll come back to that later in the talk. JWST has also done great things in the solar system. To pick one example, there are recent results just in the last few months from Pluto's moon, Charon. Pictures in the top left here in an image from New Horizons, the probe that flew past the twin system. But in JWST, it has the capability not just of taking images, but of doing spectroscopy, of splitting the light out into its constituent wavelengths. And if you do that for Charon, what was discovered was that the moon has a rich source of carbon dioxide, which was expected, but this icy moon also has a layer of hydrogen peroxide on it, which was completely unexpected. And we think what's happening here is that sunlight, even in the outer solar system, a place where it never gets brighter, at noon on Pluto, it's about as bright as it is here about half an hour after sunset. It's a place where the sun is never bright in the sky, but the solar wind and radiation may be enough to change Pluto's surface and release this volatile hydrogen peroxide that collects on the moon, on its moon, on Charon. Pluto, of course, is not a planet. We can talk about that later. But I did want to mention it as an example of the kind of thing JWST could do in the solar system. So why does shifting to the infrared? I've said it shows you the cool parts of the universe, but I don't want you to get the impression that these distant galaxies are visible because they're cool. They're visible because the universe is expanding. And so we have a picture, as I've mentioned in my previous lectures on cosmology, where we think there was this thing called the Big Bang 13.8 billion years ago that we don't understand. And ever since, the universe has been expanding. And what that means is that light emitted early in the universe's story, as it's traveling through the universe, one way of thinking about it is that it's stretched by that expansion. And so if it's stretched, its wavelength increases. And so light that's emitted by, say, bright stars in the ultraviolet early on in the universe's history, by the time we observe it 10, 11, 12, maybe even 13 billion years later, will have shifted all the way into the infrared. And so we have to go to these wavelengths to see these distant sources, things that if it were happening next to us, we'd be able to see with our own eyes or with Hubble. We have to go into the infrared. It's inevitable. And so that's why we get this rich background of sources in this image. They are the most distant sources of all. And that's what caused me to rewrite this lecture, because there's one source that I mostly want to talk about, which was found in observations that were just taken in April and that were announced to the world last week. They're part of this object was found in a large survey. It's a part of the sky that astronomers know as the cosmos field. It was studied by previous telescopes. This is a small chunk of it. And almost every dot you can see here is a galaxy. I should give you a general guide, actually. I should say, we'll go back to this one. There are a few stars. There are 2 stars in this image. The most obvious one is the top left. And stars develop these spikes in these images. Now, those aren't real. That's what happens when you have a point source and a complicated optical system. If you look at the telescope, which here has a giant sunshade, this has an SPF factor of 1,000,000. That's a real number. That's an actual measurement, which keeps the instruments and cameras cool. But you see the telescope has these struts, and it's those struts and their effect on the light that hits the mirror, hits the secondary mirror that's out on the end here, and then back to the telescopes, to the cameras and instruments in the middle, that produces this distinctive JWST pattern. And what's nice is, because the mirrors are hexagonal, they've actually tuned the optical system. So there would be an extra set of spikes there, but they've managed to hide them in the gaps between the hexagonal mirrors. So it's really careful and precision engineering. Now, As I said, I'm going to show you the most distant galaxy that we've ever seen, something that no one had seen until a week ago. As a reminder, of course, we live in the Milky Way. We see our galaxy projected on the sky, and we deduce from the observations we can make that it's this system of about a few 100 billion stars, in our case a spiral galaxy and so on, but we're used to sort of beautiful representations of galaxies like this. Now, if we go back to the cosmos field, every dot here is a galaxy. That's okay, we can zoom in. Sort of that sci-fi enhance thing, which is nice. And you begin to see there are a few blobs here. There are some peculiar galaxies, but I'm now going to circle the most distant galaxy, and this is the most impressive moment of the lecture. So I need you to be impressed when I tell you that this is the most distant galaxy. Now, I sense that there was some laughter there, and so I sense perhaps you're not impressed by the fact this is a small red dot. Astronomers have started calling these things little red dots, so I have zoomed in one more time for you. So this is the best image that anyone could ever show you of this new galaxy. Better? This field of science is often called blobology. This also has a strange name. So this galaxy is known as MOM7Z14. This is both a terrible name, I think it's not very memorable. It's better than previous attempts to find the most distant galaxies. One team named their candidate after Cristiano Ronaldo for some reason, I think in a desperate attempt for publicity. I might, if it's all right with you, I'm just going to call this one Cuthbert for the evening, because that's how I've come to think of it. I think it's friendlier, it's easier for me to say. So, how did they pick, out of all of these galaxies, how did they decide to zoom in on Cuthbert? Well, the first reason that people thought that this was a distant object was because of a technique called dropout. So, I've been showing you color images until now, but actually, the telescope takes images with filters that are sensitive to different wavelengths. It's like having a camera that records red light, one that records green light, and then one that records blue light. When you look at those images individually, instead of combining them to form a nice red dot, you can see we've still got a blob in 4 of the images, but then it pretty much disappears at the shorter wavelengths. And so what's happening here is this is an effect of that expansion of the universe. Imagine we had a light bulb in the early universe that emitted only one frequency of light, let's say in the ultraviolet. We'd see it in the ultraviolet there. As the universe expanded, if we saw it a few billion years later, we'd see it in the visible, it would move to the red, and then as the universe kept expanding, it would move to the infrared. So because we understand stars, and when we talk about light from galaxies, we're really talking about light from stars, then we know that there's a point where we should see this dropout when it should disappear. So I could show you it as a spectrum. So if I smear out the light so it's a wavelength, so it's a rainbow, so short wavelengths are over here, so your blue end is here, and your red end is here. You can see the galaxy gets brighter, and then there's this sudden drop down here. And this is a combination of dust in the galaxy that blocks this bright light, and also hydrogen, both in the galaxy and in the universe, that blocks this out. So this is very common. And so what we realize is that we've got a galaxy that maybe has this shape in its spectrum and that has dropped out. What's nice is, though, that because of JWST, this spectrum also exists, and we can recognize, and you can see them labeled here, features in the spectrum, fingerprints, that are due to the presence of atoms like carbon and nitrogen in particular. And we know what wavelength they would be if you were in the lab. If you set up an experiment on a bench and you made carbon and nitrogen shine in this way. And we can see what wavelength they're at here. And so we can measure how much of a shift there is. And if you put that together, what you realize is we're seeing something that perhaps actually looks like this. This is a nearby ultraviolet bright galaxy, but which we're seeing as it was, that red blob, we're seeing as it was 280 million years after the Big Bang. So we're looking back more than 13.5 billion years of cosmic history, right back to a time when the first galaxies were forming. And we can be confident of that because of the observations that we've got from JWST. What's particularly interesting, though Cuthbert is the record holder, what's interesting is that we've begun to find a whole category of galaxy like this. The previous record holder, until about a year ago, was another red blob. This one's got sort of a nice structure to it, perhaps, if you're a connoisseur of these things. This was called GNZ11. This was found in a Hubble Space Telescope image, and there are a couple more as well. Here are 4 of the most prominent ones. There's a red blob. Glass Z12 GHZ2 has the worst name, but is still a red blob. Jade's GS Z140 was the subject of this lecture until last week, and is a red blob with an extended bit, and then we've got Cuthbert on the end. And this shows redshift, so this is a measure of distance and how bright they are, and we're beginning to fill in. All the other dots are things that we knew about before. So the point is we're beginning to fill in a completely new part of the spectrum of this parameter space. We're finding that the early universe unexpectedly has hundreds more of these things than we thought, because we're finding them even in our first look at tiny patches of the sky. Now, some things do make sense. These are blobs partly because they're small. They're physically small. And that makes some sort of sense. We have a theory which predicts that those things should be small. It's a theory that starts with the oldest light of all. If you look at the cosmic microwave background, subject of a previous lecture last year, this is a whole sky map, and it shows tiny fluctuations in light that was emitted just 400,000 years after the Big Bang. So this is our earliest view of the universe, and it shows that there are places that are more and less dense than the average. Over time, gravity acts to exaggerate those differences. So in a supercomputer simulation, if I start with this universe and then run it forward from 15 million years to about a billion years after the Big Bang, to almost 5 billion years after the Big Bang to today, what you can see is that those tiny fluctuations become more exaggerated. What starts off as pretty smooth becomes lumpy. This is the role that gravity plays in the formation of the universe that we see us around us today. But I think if I show you these stills, then it sort of looks like a nice, calm process. You know, like, I don't know, something settling into the bottom of a jar or something like that. But if we look at the movie version, and in this movie, and indeed on those stills, I took out the expansion of the universe, so we don't have to worry about that. What we see is something much more chaotic. So this is a universe simulated in a computer where you can see that each blob here, which might be a galaxy or a cluster of galaxies, they're engaged in an interactive dance with each other. They pass each other, their gravity affects each other, they merge, they collide, they form these big clusters like the one I showed you in the very first image. And so if you then stop this movie, play it one more time, but if we stop it in the present day universe and say, okay, what's the history of any particular galaxy? You could do this and you could say, what's the history of the Milky Way galaxy, for example? The answer is it's a chaotic history that involves lots of mergers, collisions with other galaxies, something that I discussed during my lecture on Gaia a few months ago. And in fact, you can represent this as a merger tree. So this is the history of a galaxy down here at the present day. And then this is sort of the family tree of every galaxy that's merged to form a single system today. And so what you can see is that there are about 40 different systems that start off life in the early universe that come together and merge to form a single small galaxy today. And so what we should expect when we look at the early universe is we should see lots of small proto-galaxies, the things that will go on to be the building blocks of the large galaxies that we see today. So it makes sense that these things, all of them, are small. That's a prediction that we like. But the problem is that these simulations that I keep showing you, beautiful though they are, tell us how many of these things should exist at the beginning. We have a good theory of cosmology that rests on the fact that these simulations match our observations today. And we have a discrepancy. We find 100 times as many of these things as you'd expect, as anyone expected before JWST started doing these observations. So one possible consequence of this is that about a third of my lectures that I've given you are complete rubbish, in that we need to completely rethink our theory of cosmology. But before we do that, I think we should ask ourselves what else we can know about these galaxies. Are there other things going on that might explain their sudden prominence? And one thing you might say is that, well, you told us that these are proto-galaxies, the things that will merge to go on to form things like the Milky Way. Well, is there any sign that they're merging? If we look in the local universe, we see spectacular mergers. This was one of the first images released from JWST. This is the object known as Stephan's Quintet. There are 5 galaxies there, 2 at the top, there's a double there, and then 1 at the bottom, which turns out to be an innocent bystander. So it's really Stephan's Quartet and a hanger-on. If these look familiar, by the way, and you're not an astronomer, they also play the role of the angels in the start of It's a Wonderful Life, which is my fun fact for the evening. But the point is that these things are disrupted. You can see signs that they're merging with each other. They have these long tails. They're actually forming stars rapidly. That's the red patches there. And you can see there's actually faint tails of gas spread out between the galaxies that's been ejected from these violent collisions. We can see this more so in local galaxies. This is the terribly named IIZW96 merging, I guess 2 ZW96 merging galaxies. This is the Hubble observation, and we can overlay the infrared JWST image in a sec with a bit of dramatic spin. There we go. But you can see this is not a normal galaxy. This isn't a nice stately disk like the Milky Way. It's not a big ball of stars like an elliptical galaxy. This is a mess. And so we should ask whether there's any sign that Cuthbert looks like anything that's been disrupted in this way. We can ask whether it's non-symmetrical. And so Rohan Baidu and co, who led this paper that made me rewrite the whole lecture, thank you. They also sent me the pictures, so that was good. Did this properly, so they took for each of their little images of the galaxy at the top, they created a model. They said, okay, we're going to assume this thing is a sphere, and we're going to insist it's the same model in each wavelength, and we're going to care about how it would look in different wavelengths, and then you take the model away from the data, and anything that's left at the bottom should be a sign that it's asymmetrical, that maybe it's been disrupted by a merger. And as you can see, astronomy is about making simple measurements well. There's nothing at the bottom. In other words, all the light that we get from this blob can be properly explained by having a compact sphere with no asymmetry. So there's no sign that this thing was a merger at all. Compact fits, we said these things should be small, but we're not sure that there's any sign here that this is a merger. And actually, it's a division between the little red dots that we found. The previous record holder, Jade's GS7Z140, which I really should have renamed, maybe we'll just call it Jade, obviously does have this sort of disruption. So that one seems to have had a merger, but that's not a universal thing. What else can I tell you about this blob? Well, one of the arguments that's going on, especially once you realize that it's compact, is whether what we could be seeing here is light from material that's falling into a central black hole. All galaxies in the present-day universe have a central black hole. We know that the Milky Way does because we can watch stars in motion around some mysterious object at the center of our galaxy. So this is 20 years worth of observations from a telescope in Hawaii, looking at the motion of stars in the galactic center. And what you can see here is that they orbit, particularly this one, SO2, orbits a star that's in the middle. Orbits an object that's right in the middle of the galaxy, which weighs about 3 million times the mass of our sun, and which must be smaller than the orbit of Neptune. And science tells us that that has to be a black hole, that nothing else could exist at that density. It also behaves like a black hole. So we can play this trick with some of the early galaxies. JWST can look not at how stars are moving, but how gas is moving in the center of these galaxies. And when that happens, you get a spectrum, you look at a wavelength, and what happens is it's broadened. You end up with, instead of just all appearing at the same frequency, you get a broad line. And this is clear evidence that this particular galaxy Sears 1019, another of these little red dots, has a black hole at its center just 570 million years after the Big Bang. So this is twice as old as Cuthbert. But this has led astronomers to say, okay, what we're seeing here is it's nothing to do with the galaxy. We're just seeing the very first black holes feeding dramatically, rapidly, on abundant material that exists. Now, that itself is a challenge to cosmology. We didn't expect such black holes that early on, and astronomers have invented a series of plausible models, some of which involve the first stars being very massive and exploding to produce large black holes early on, or perhaps the first galaxies being dense enough that they can collapse material at their center to form a black hole directly, and some less plausible, like mysterious dark matter that sits at the center of a star and manipulates it to form a black hole, which is a fun idea that we need not talk about more. But this looked pretty good, I thought. I went looking in the literature last week to see how this idea was holding up. Maybe what we're seeing here is the growth of black holes. I saw a paper at the top left which put forward exactly this explanation. Then on the same day, a paper at the bottom that says this is definitely not what's happening because we haven't seen any X-rays coming from galaxies like Cuthbert. We should see X-rays from hot gas falling into the black hole, and we don't see anything, and we really should have done. So we don't think that this galaxy has a dramatically growing black hole at the center. That's not what's going on. We need still, the rest of my lectures and all of cosmology are still under jeopardy. What we need to do is think about alternative explanations. So let's think about what we're actually seeing here. When I say we're looking at light from a galaxy, I've already said that what we're really looking at is light from stars in that galaxy. And we can study stars close up, of course, in the Milky Way. This is my favorite JWST image. This is actually an image of a place in our galaxy, like the Eagle Nebula, which I showed you to begin with, where stars are forming. So what's happening here is that at the top you have a cluster of young, bright stars that have formed, that have emerged from this dust, and their light is slowly eroding away these cliffs. This is another image I could give an hour-long lecture on. You can see there's all sorts of things going on down here where the clouds are being shaped by the winds of those young stars, so they stream away from the brighter stars at the top of the image. But long study of star-forming regions like this have told us that even though they look complex, almost biological levels of complexity, you know, in terms of this is gas and chemistry and all sorts of complicated things that physicists shy away from normally happening, there are some fundamental rules. And one of the rules that seems to hold in the local universe is that whenever you have a cloud like this that's forming stars, it will always form the same kind of stars. Or in fact, it will almost always form the same range of masses of stars. So the ratio of, let's say, stars like the Sun, which are in the middle of things, the ratio of stars like the Sun to dwarf stars that are maybe 1/10 of the mass of the Sun, and the ratio of stars, the mass of the Sun, to big supergiant stars that might be 200 or so times the mass of the Sun, that spread is always the same. It's always dominated by the smaller stars, but that pattern is always the same. And so that's really useful, because that means that I know when I look at a galaxy and I measure how bright it is, it means I know what type of stars must be contributing. And so I can work out how many stars must exist in any given galaxy. So I can take something like, I don't know, the Large Magellanic Cloud. This is one of the Milky Way satellite galaxies. It's one of the galaxies that we're eating in this merger process. And it's about 1/10 of the mass of the Milky Way. And I know that because I can add up the light that we're getting, and I can say, okay, I know what stars are contributing, and I can get that number out. And because it's local, we can check it, which is really useful. Now, we can play the same game with Cuthbert. We can assume that we're forming the same kind of stars, and we find that it's not a massive galaxy at all. It's about similar to the Large Magellanic Cloud. It's about 1/10 of the mass of the Milky Way, which is kind of mind-boggling that we can see this galaxy right back at the dawn of cosmic time, and it's only got 1/10 as many stars as we have in the Milky Way. And we could even, by studying its color, say things about when they formed. We know, or we know is too strong. There is evidence, that's better, otherwise I've got to rewrite this talk next week. There is evidence that we're seeing the peak of a burst in star formation, that we have really young stars there that are only maybe 10 million years old. And so we're seeing perhaps a burst of star formation, a firework display, not the underlying rate. So it's possible that when we say we're seeing too many of these things, what we're really saying is that they form in bursts of stars, that there's some process, perhaps how they interact with their surroundings or interact with each other, that creates bursts of stars. And that we see them when they flare up, and if we waited a few million years, this would fade, and then a different galaxy would appear, taking its turn in the limelight. There's one more set of clues, though, that we have about this galaxy. Because we have the spectrum that I showed you, and I said we have those lines of carbon and nitrogen that let us measure the distance to this galaxy, that also tells us that as well as the stars that are there, there's gas. We kind of knew that because that's what you form stars out of. But we know that there's lots of gas there, and we can say something about what it's made of. In fact, we know that it's very nitrogen rich compared to anything we see in our galaxy. So there's more nitrogen than carbon. Again, I think it's remarkable we can make these statements about a blob, right? And I can tell you things about it. So some process has produced more nitrogen than carbon. Now, that process must be star formation. We know, as every astronomer is compelled to tell you, that as Joni Mitchell said, we are stardust. All the heavy elements that make us up, everything that astronomers call metals, everything except hydrogen and helium, perhaps a sprinkling of lithium, which were produced in the Big Bang. Everything else was made in the cores of stars or in the explosions which end their lives. And so the fact that this galaxy has nitrogen and carbon tells us that a previous generation of stars has already formed in the 280 million years between the Big Bang and this galaxy, has already formed, lived, died, exploded, and spread its material through the galaxy. And the fact that it's nitrogen rich tells us something about what that first generation of stars must have been like. There's another place in the universe where we see this chemical signature, and it's much closer to home. This is a JWST photo of a globular cluster called M92. They didn't want to look at the middle because it's too bright, so here's a local image. So you have to imagine that there are about 300,000 stars in total in this cluster. It's part of our galaxy. But it's a long way away. It's about 26,000 light years away on the other side of the galaxy. It's about 40 light years across, and as I said, has about 300,000 stars within it. It's a spectacular object, and this image from JWST was taken to help astronomers look for the lowest mass stars. We want to know how puny a star can be and still be a star. But it also allows us to do beautiful zoom-ins like this one into that star field within the cluster. Now, in this star field, and I apologize, I didn't find out which ones they were, but in this star field, there are some of the lowest mass stars we've ever seen. They weigh in at just 0.08, so 8% the mass of the sun, and yet they're still there. And we care about them because the lower the mass of a star, the longer lived it is. It's sort of counterintuitive because you'd think that the more massive stars would have more fuel, and so they should last longer, but they have higher temperatures at their center, so they burn through that fuel faster. And so actually it's the puny stars that last longer. A star 10 times the mass of the sun will live for only a few tens or maybe 100 million years. The sun lasts for a few billion, maybe 10 billion years. And these small stars that are in this image are effectively immortal. They will last for 20 or 30 billion years or so, and will be the last stars in the universe to die. But the chemical makeup of low-mass stars in these globular clusters, like M92, which surround the galaxy, match that of Cuthbert pretty well. And so we begin to put together a picture where what we're seeing here isn't the formation of a whole galaxy, but might be the formation of the first cluster of stars around a galaxy, which will go on to evolve and develop and form something perhaps like the Milky Way, surrounded by a retinue of globular clusters. All of which I think is quite an impressive story to get out of a blob. But it's a blob that we can study with this expensive and fascinating instrument. Now, why have I told you all of this? This is a sensible question, I think, because the odds are that this galaxy, in 6 months' time, perhaps even tomorrow, will be beaten. It will no longer be the most distant galaxy we've ever seen. And one of the things we're discovering is that each of these galaxies seems to have had a different existence. Some do show evidence of mergers, some show evidence of black holes, some have different chemistry. And actually, the long project of JWST, when you look at a field like this, and this is one field of the sky from one project, and realize that each of these individual galaxies has had its own history, even within the first few 100 million years. It's only by piecing together those individual stories from each galaxy that we'll actually be able to work out what's going on in the early universe. And then it's only by doing that, by listening to each of these individual galaxies, that we'll be able to piece together the story of how the Milky Way came to be, how we came to form, how our part of the universe evolved through this period that we can now examine for the first time with this telescope. And whether we end up in a world in which what we decide is that we're seeing the formation of these globular clusters, whether we're in a world where we discover that actually this rule that star formation always produces the same set of stars doesn't hold in this early universe, and maybe there we're forming more large stars, and that breaks this rule, and so these things aren't as spectacular as we think. Or the result lots of us would like, maybe it's just that cosmology is wrong and we've got to start our fundamental theory of the universe all over again. We're only going to work that out by paying detailed attention to blob after blob after blob. And I think the nice thing about this is that looking at the starfield, that's the same, I think, as how I want you to think about these big projects. It's very easy to talk about these projects as if they're one person's idea. And when I started writing these lectures this year, whether it was the probe to go and look at the sun, the Parker Solar Probe, or whether it was a mission to an asteroid like that showed us asteroid Lucy, or whether it was the Hubble Space Telescope or JWST or Gaia, or even the marvelous gravitational wave observatories that I talked about that show us ripples in space-time, I found myself writing the standard stories of science where you say, this person had this idea and isn't it marvelous that we now know that? But actually, just as we can only understand the universe by adding up each individual galaxy's story, any of these projects takes thousands and thousands of people. And so only by taking their collective effort and working together do we get to a point where I can tell you, stand on a stage here and tell you about something that we just didn't know about a week ago. And we need to remember, it's like we're at a time where these projects, which are fundamentally international, JWST is American, Canadian, European, with other contributions from people around the world, are under threat. Most obviously in the States, where NASA's budget is threatened with an enormous cut, but also throughout the rest of the world at a time where people are looking for projects they can put their flag on instead of one where we can work internationally. And so I think it's a good time to be reminded that if we work together and build these marvelous projects that exist, yes, because they provide science jobs, and yes, because technology development is driven, you have better cameras because we decided to build space telescopes, but mostly because it's fun to stand here and think about a blob. I finished last year's lecture with a poem from Rebecca Elson, who is an astronomer and an astounding poet, and I want to do the same again today. This is Rebecca Elson's poem called Let There Always Be Light. For this we go out dark nights, searching for the dimmest stars, for signs of unseen things, to weigh us down, to stop the universe from rushing on into its own beyond till it exhausts itself and lies down cold, its last star going out. Whatever they turn out to be, let there be swarms of them, enough for immortality, always a star where we can warm ourselves. Let there even be enough to bring it back from its own edges, to bring us all so close that we ignite the bright spark of resurrection. Thank you very much. I shall see you next year.